Hi guys, I'm Knud. I work at Fractal, and I'm going to talk about some embedded Linux bug hunting. So what does that mean? Well, in this case, it means how you would identify and exploit a bunch of bugs in a quite wide range of UniView IP cameras. So I'm going to talk about how you get from having a camera in a box to landing a shell on the actual camera, and where to go from there, and then maybe discuss some exploitation strategies, why you would do something and why not. And in my opinion, the workflow is applicable to most IoT devices. At least I just did what I normally do when I get something, right? So it doesn't really matter that it's a camera. But a good reason for targeting cameras in particular is that they're not going to go to the cloud. They have to stay on-prem, at least for the foreseeable future, right? And camera wires, I have some red teaming background, and the camera wires, they often dangle out of buildings, and that makes them, in my opinion, quite a juicy target, because you can cross the trust boundary from you being on the outside of the building to being on the internal network, depending on how it's set up. And I don't audit cameras for a living, so it's good to have a distraction from actual work. I don't know if any of you are familiar, but I'm incredibly productive when I procrastinate and do something instead of the thing I'm supposed to be doing, right? So I can really get a lot of stuff done when I do two things at the same time. I think it's nice to have some softer targets to poke at, because it's good to get some wins once in a while. It doesn't always have to be remote kernel exploits or something. Sometimes it's nice to just get a shell. And I think in this case, practicing on something like embedded Linux devices means that you can abstract away a lot of things that you don't have to care about. You don't need to worry about weird real-time operating systems or other strange things that make things complicated when it's just Linux and it's just software running on Linux, right? And that means that you don't have to worry about a lot of layers of complexity. You can just say, for example, the IP stack. You don't have to worry about it because it's just there, and it's the same as all the other IP stacks on all the other Linux devices, right? And it also allows you to get some mileage, right? And I think practice makes perfect, obviously, and reading 10 write-ups about bugs on the internet will not give you a tiny bit as much experience as actually finding some bugs in some things and writing some exploits and overcoming some challenges that way, instead of reading about how other people did it. And also, I'm not really a fan of cameras, so I think they're a great target to screw around with. So what I normally do when I get an unknown device, or buy an unknown device, I open it up and take a look inside and see what's what. In this case, the camera looks like this. This model is called a bullet cam. You take it apart very carefully, I might add, because there are quite delicate ribbon cables inside that can break or become loose, and then you need to place your device in a very specific way on the table for it to boot and not time out all the time. It's a ball grid array mounted nightmare, which means that desoldering the chips is definitely out of my league, because, well, I can take them off, but I cannot put them back on, and that's like sort of just destroying things. But when you look at the chips, you can see that it's a high silicon IPC SoC. What does high silicon IPC SoC mean? It means that it's an IP camera system on chip. And what is a system on chip? Well, this diagram actually shows what's inside the black chip in the middle, right? So there's some memory and some hardware video decoders or encoders, sorry, some hashing functions, some UARTs, some general purpose I/O pins, and all that stuff. So it's basically a camera or a computer with a bunch of hardware doohickeys crammed in a very little package. So when when you want to start looking at it, you need some sort of access to look on the thing. And I prefer, well, I really like it if the device has a UART console, because they're very easy to identify. In this case, you can see in the bottom left corner of the PCB, there's 4 pads that probably is a UART. It's a lot easier to look at the UART console than it is to desolder the flash and dump the flash, because there are no rules for how the flash is laid out. So it could be encrypted, and it could be all sorts of stuff. If you can get a UART shell on the thing, then it's a very solid start. I'm terrible at soldering, but that doesn't really matter, right? Because in the top right corner, as you can see, I have just attached some weird plant wire to the PCB. That's enough to make the electrical connection. And even if you short them a bit or do other things, I mean, you are less likely to screw up anything than if you are bad at soldering like me, right? But this is enough to make the electrical connection and see that the UART console is working. And with that, you can get a lot of debug output, and maybe sometimes, if you're lucky, you can even get a shell on the device, and that's a very good opening. So UART is really everywhere, because I went to my junk shelf and looked at stuff I've accumulated over the years that I no longer use, but I've hacked on some of them and so on. And I looked at how many of them have UARTs, and it dawned on me that everything on the shelf has a UART, right? They don't all land you in a usable shell or something, but the UART shell is, if you remember, like old Cisco routers and sticking in a Cisco console cable. It's the same level of access, so that you may land in a real shell or you may land in some restricted garbage shell that is not as much fun, but it will definitely be useful for troubleshooting and debugging something, right? And in the case where there is no UART, maybe you can do some other things like JTAG interfaces with the chips and whatnot. I prefer the UART because it's easy, and the adapter costs €5 or something, right? So, with all that talk about UART, when I ordered this camera, and I didn't end up using the UART because I was looking at the firmware instead, and the vendor side is not open at all. You actually can't go to the vendor side and say, I want a firmware update for this and that specific model, right? But some third-party sites do have extensive collections for these cameras. And it's also good to be looking at the firmware because, as I said before, maybe there's no easy UART or a usable UART, right? It could be that the boot environment is hardened. It could be that there's a root password that you don't know and you cannot boot it in single-user mode, and so on and so on and so on, right? So it's also good to be able to look at the firmware. Pretty straightforward for this particular case, luckily. So when you look at the UniView firmware contents, it has, and this is also quite normal, there's a zip file, and inside the zip file there's a blob, and in that blob you can run tools like binwalk or something to try and identify file systems in it. For this one, you don't even have to run binwalk because there's just the program.bin, which is a UBI file system that you can unpack cleanly with tooling called UBI dump. But you're going to end up with the same as if you ran binwalk on the thing. So it unpacks it, and you can start probing or looking and figuring out how things work, right? And in this case, there's a script called init.sh. That's a pretty telling name. Looking in that one, it spawns some other script, and that one spawns some binary, right? And then it backgrounds that binary, and that looks like the main service or the device startup point where it's going to hand over execution to that one, and then the device will be operational. So, easiest thing in IoT reversing, find references to system or other wrapper functions, right? In this case, I just put this huge binary into Ghidra, look for calls to system, of which there weren't a lot, but that turns out that it's because they made their own wrapper function, which then calls system instead, and that's very common. In this case, there's actually a few different routes to system with different names, but in the end, they all call system. Don't ask me why, it's just how it is. But looking at this, if you know the iSCSI admin command, the things after the -t and the -p are normally user specified because you can do some iSCSI administration and use it as storage for your camera, so you can offload the video. So pretty good. I'm ready to compromise the device as soon as it lands, right? But I get the camera and I connect it, and I'm so ready, running from the mailbox to my computer, and I can't find out how to trigger the bug. And it turns out that my El Cheapo bullet cam is clearly not meant for enterprise environments where iSCSI setups are common, so it doesn't support iSCSI for the storage. And very sad. And when you look at, well, I'm not going to go into detail with that, but the way it's built, the software architecture is a bit weird, so it's not very easy to find out how to actually trigger the bug without doing a bunch more reversing, which I wasn't that interested in at that point. But looking at that web UI, I get some hints that it supports some other things, right? So it has NAS storage, and then you look at how do they handle storing data on the NAS. Well, they do pretty much the same because they take your user input and they feed it to system, and then you, in your NAS test, you give this specific payload where you put something in the password file, and then you spawn the telnet daemon, which is not running by default. And then it's spawned, and you get a root shell when you tell it to the device. So, good start. Of course, it's, well, next thing to do when you pop that shell is don't just blindly click firmware upgrade, because you might get locked out of the device in case they fix that bug. So the software update for this particular camera luckily has a feature called Cloud Upgrade. So you click that button, it's going to send a plain text request to the internet, but you can sniff it and see that this is where it's going to get the latest firmware from. And then when you look at the naming scheme, it's not trivial, which had it been simpler, maybe you could have harvested a bunch of firmwares that way, but no dice in this case. But anyway, take the new firmware apart before applying it, see that your bug is still present, and then apply the latest firmware. Because from experience, there is nothing sadder than bug hunting on old releases and thinking that you pop shells and you're the master hacker, and then you update the firmware and nothing fucking works because, everybody, all the bugs are fixed already, right? It's very sad and a huge waste of time. So try to work on latest, greatest instead. So post-authentication shells, so I had to log in to exploit that bug. It's not the best, right? Because boohoo, the admin can do bad things to the thing. I mean, he probably can anyway in one way or another. So at the same time, if you look at web interface bugs, they are a little bit shallow because you can run burp and find some command injection bugs. As a side note, that's also incredibly dangerous if you just do spider and scan with burp on these devices, because you can most likely ruin it and then you have to buy a new one. Because if you put in some bad input in some of the fields and it gets written to NVRAM and it tries to read some garbage value at boot and it doesn't read what it expects, and then it reboots and so on and so on and so on, then you've basically destroyed the device. That is very much a possibility. So I would be very careful before just doing spider and scan to find these bugs. Anyway, they're shallow and they're easy to find, which means that your great bug could be known to many other people, and that's never very nice. So to get better understanding of the device, you do some attack surface analysis. It's not essential to have the real device. So far, everything I've done could have been done just by looking at the firmware, but it is a lot better to have the actual device, because maybe you've missed something. If you just look at the firmware and you say, there's a bug in this service running on this port, maybe it's firewalled off when it's running on the actual device, right? So a real device and a real shell is extremely useful, and at the same time, when you look at the Uniview firmware updates, this program.bin has programs and stuff, but it doesn't contain the base Linux system. And where would you place a backdoor account? Well, in the base Linux system, right? Or other mistakes. So it is definitely best to have the real device, and it's a lot easier to do that sort of analysis dynamically in a running environment instead of statically on a bunch of files. Also, comparing netstat to Nmap, if you port scan this camera, you will see that there's 2 open UDP ports and a bunch of those filtered or unknown services that we all know and hate from the Nmap output. But when you look with netstat on the running device, you will see that there's actually 6 open UDP ports. So if you look at the TCP services from the device as part of mapping out the attack surface, because, well, we want remote attacks, right? There's a bunch of services listening on localhost and other weirdness, but those you just filter out and say, this is the actual attack surface from a TCP service point of view. So there's probably a web interface on port 80, and then some RTSP on 554, and so on and so on. So some of the ports are well known. Some of them are a bit more up in the air, like what's on port 81. Well, probably another web-based interface, right? But that's for you to find out somewhere down the line. So looking at the UDP services, it's still this Mwareserver running a lot of listeners on a lot of ports. And then there's something called maintain running some service as well. So when you look at the Mwareserver, there's not necessarily any good way of finding out what each port is. Well, you can run Nmap and try to do some service identification, and it'll say this is an HTTP interface, maybe, but that could also mean that it's some weird SOAP service or other protocols on top of HTTP. And if you do service identification of one of these, I don't remember which one, Nmap service identification is going to crash the Mwareserver binary, and it's going to cause the device to reboot, and that will give you very inconsistent results when it crashes in the middle of your fingerprinting. So a bit of probing of the different services will lead you to a list like this, that the OnVIF service is running on top of the HTTP interface, and that it runs 2 more OnVIF services that are just broken / non-functional and cannot be configured in the UI. And when you look at the UDP services, it's a little bit easier, and you can quickly find out that, well, it's SNMP and some other things, right? So that's easier than the TCP services, because what you can do when you want to look at the UDP services is that you can set a breakpoint on the receive from function, which is one of the ways to receive UDP data, and then just send some UDP data to the port with the breakpoint set, and then view the backtrace, and then you can see that this port is clearly tied to this module in the call stack, and then you'll find out that this weirdly named module is actually net SNMP compiled as a shared object and called from the binary, right? But the Mwareserver itself is a big monolith master app which runs everything on the camera, and then it has some stuff inlined and some stuff in shared objects. But once you start making lists and finding out what's what, then you can just focus on the individual components and just start doing regular auditing, right? Which means understanding how things work and taking notes and so on. The ONVIF interface, it's Open Network Video Interface Forum. It's an XML-based protocol running over HTTP. And you can call a few unauthenticated options or operations on the service, like it has to support the get services call because that's how it says what services it provides, and then you can get some capabilities and some system data time. So nothing too interesting from an attacker perspective, except the system data time can be useful for the next one at least, because when you look at the web interface, something like this, the option 2 here, should get your spider senses tingling, because when it says that you can email the device serial number and date to somebody and get a temporary password, that means that this temporary password that you can get from them, the device has a way of validating whether this password is correct, right? And if the device can validate it, it means that it can also generate the equivalent locally, which means that you can take it apart, find out how it generates the password, and then you can generate the passwords for the device. So you can do WS Discover, and it will give you the serial number, unauthenticated, of course, and now the post-auth bug that I didn't like too much before is actually useful again, because now I can bypass authentication, right? I can make my own password with this and get in and exploit command injections in the web UI without knowing the real password. Looking at how the algorithm is implemented is not too interesting, but it does use the device serial and the system date for this function, and it generates 6-character lowercase and digit passwords, so they're not even that interesting. And if you had a very fast link and a very fast camera, well, there's a bit over 2 billion candidates, right? So the Mwareserver also supports SNMP, and if you think about SNMP, which is Simple Network Management Protocol, something that you normally use to pull statistics off interface counters and whatnot to draw traffic graphs and things like that. At least that's what I normally use it for. And you put on your thinking hat and say, what could go wrong with SNMP? Well, something that could go wrong is that normally you communicate with it with, let's call it a shared secret, just to make it basic. And you need to know the secret to be able to get the data. So how can you do that in a bad way? Well, you can have a pre-configured secret that's the same for all the devices, right? And yes, they have decided to do so. If you go back one firmware version, there is no option to configure the SNMP in the UI. It's just enabled, and you cannot turn it off, and you cannot configure it. But they have decided to ship it and not let you do anything with it for some reason. What else can go wrong with SNMP? Well, it could be spilling secrets that it's not supposed to spill, and it also does that, because when you SNMP walk this just the device and say, give me all your counters, it in the output it gives this ISO 3614 and then you try and walk that one with a few octets shaved off, and it will lead you to something else, which will give you the admin or the MD5 sum of the admin password. And that is not a part of the net SNMP source code, I can tell you that much. If you look at the console, it at some point says that it is adding a read-only user to the SNMP config. That's a lie. It is read-write, so you can actually, if you're so inclined, you can walk it to make sure that the bug's there, and then you can SNMP set a new password to that OID. You can log in, do your thing, exploit your post-authentication command injection bugs, and then set back the real password, and the admin will be none the wiser, because even though you've reset the password to something you know, you've also set back the old one, right? Ta-da! And then something very important, looking at the UDP service, it's on this port, it's implemented in something called libp.so, which holds a lot of core functionality from the camera. And I looked at it, and it's some IPC mechanism where the programs talk to each other, and for some reason it's network bound. And I looked at it, and it was not too interesting, and it was also pretty complex to find out how it worked, because some of the code had been inlined in some weird way, so I definitely didn't want to spend too much time on it. Luckily, I compared it across a few different firmware versions, and it wasn't present in all of them, and not in all device models, so I could just give up on it, right? And that can be okay depending on your objectives, because it depends what your goals are. Are you auditing this device for money, or are you auditing it for fun? Because if it's for fun, you can just give up. And do you want to find all the bugs in it? You should if you're getting paid to audit it, right? But if you're doing it for fun, maybe it's enough to just find one bug and write one exploit and pop one shell on the camera. So I think it's definitely okay to give up once in a while. So putting that terrible big binary behind us, looking at the one outlying service called maintain, I think a few good reasons for targeting it is that it's a weird name. So it's not a standard process. It's something that they have implemented, right? So it's UniView specific. It sounds like something somebody left behind by accident. It's a very small service, so it's easier to do some static analysis on the binary without going crazy, because you can actually finish before the sun burns out. It's UDP, so you can spoof sources and send pew-pew packets without them knowing who is hacking them, or is hacking the camera. Nmap doesn't know what it is. That's also a very good sign, because that means that you can't just blindly go towards it and expect anything meaningful. So you'll actually need to apply some thinking to audit it, and that means that the bugs are less shallow and less findable using standard let's find all the bugs tooling, right? So doing that, pulling, this is Ghidra's pseudocode decompilation view, which is NSA's greatest gift to the internet, if you ask me. So what you're looking at here is just a very common network service pattern. So it runs an infinite loop where it says, is there any data? If there is, break out of the loop, and if not, then sleep, and then look for data again. And then when you look at the function call to receive from, this is what I mentioned before as well, where it's this is how it's receiving the UDP data, right? And looking at these, it's all a bit confusing and nonsensical, of course, but, and this is the one proper reversing tip, or the real reversing tip I'm going to give you. As soon as you understand what something is, you just rename it in the pseudocode view. You can press in Ghidra, I think it's L or N or something. Because then all of a sudden, if you compare these two, my input is landing in this receive from call, so it's no longer called AU stack 4464. Now I have labeled it my input, right? Because when you look at the receive from function prototype, you will see that it expects a file descriptor and the input data and some length and some flags and da-da-da-da-da. But now you can just say my input, right? And then because I renamed the top one, going down, I can see that another function is going to do something with my input, right? So because I just keep reading the pseudocode and I go down here, I can see, okay, it's actually my input again. So I can safely say that this is processing my input in some way, so I'll just call the function parse input. And then when you look at the actual message parsing code, the calls after receive from, and so it's this parse input, but then the Ghidra function prototype for the actual parse input function is just going to show you those names will not propagate because they're local to the outermost, the other function, yes. But just renaming in the function prototype in Gira, renaming param3, which I know is my input, when I rename it there, the names are gonna propagate down, and as you can see here, there's a function called logfunc. That is actually from out here where I have renamed something, the one that is fun 00011c, blah, blah. That's clearly a login function because it writes some text to something. It doesn't matter if it prints it on the console or in a file or whatever. It's clearly some sort of logging function. And moving on to the next function, this renaming has already propagated further on because it's the same function being used to log data in this other function. And as soon as you can see what something is, the left is the original code and the right is after a bit of fix-up, right? Down here where it has the default fall-through, it says error UC code C blah blah blah, and then this local 25 variable, right? But that means that from the programmer point of view, this variable is actually called UC code, so you can just rename it and follow his naming pattern, and then names will propagate and things start to make sense because when you scroll further down in the code and the things are named nicely, it's a lot easier to understand than when they have weird names like local 25, right? And then, well, keep renaming things because everything will make sense all of a sudden. This functionality, you can see that it's used for submitting some IP import combination because it says get IP import fail. And if you look at the call to ISO C99 scanf, you can see that somebody has made a mistake because they have they're reading the length from a TLV object that I specify over the network, and they don't use it as a bounce for the copy operation. The scanf call will just override everything and smash the stack. So, to be able to trigger this bug, you need to be protocol compliant, right? So you need to speak the correct language to be able to reach the vulnerable location. But because I've renamed everything, like the good reverser I am, it's pretty easy to understand how it actually works. So making a mental map of the protocol, it's something like an opcode and something unknown, and then some length fields with itself included, and some authentication data, and some other stuff. And the other stuff is also pretty easy to understand. So the TLV construct is something that you will encounter quite often when looking at network protocols. So it means type length value, right? So you have like an opcode and then length and then some values. It's very common, and once you've seen it a few times, you will see it everywhere. So for fun and or practice, I think it's a good idea to write a fuzzer for the protocol. You don't have to, but maybe because I understand the protocol and can write a fuzzer, maybe there are other bugs in the same area that are less trivial to spot because API misuse is pretty easy to spot, but maybe it could also be some inline memory copies or something that can be a lot harder to spot, where you actually have to think a lot to see if they're doing something wrong. So I like to write a fuzzer once I understand something. For boofuzz, which is like the successor to the Solly fuzzing framework, you can make a pretty easy skeleton where you say connect to this one using this request, and then this is the protocol model and the grammar that you can use with boofuzz to make it generate valid but malformed requests that are protocol compliant to this protocol, right? So for all the values, like the byte value in top where it says S byte 0x01, it's gonna substitute and put in a lot of known bits and random byte values and so on. And where it encounters strings, it has a long library of known bad string values. And the good part is that if it, so the S size on line 4 is going to update automatically once the fuzzer is inserting malformed data further down in the packet. And then you can just trigger the bug because you know exactly how to speak the protocol. And then you have some... another thing for the embedded devices is that you need probably GDB servers for MIPS and ARM and whatever. But luckily, you can then connect from your real computer using GDB multi-arch because that one understands that the debugged process is some exotic architecture. So triggering the bug, you can put some of the required protocol stuff, the correct length field, very important that it's correct, some junk, and then this malformed TLV packet with the fake length field, which is below 43, because otherwise it doesn't do the copy, and then you have the long string, and then you have smashed the stack and overwritten the instruction pointer. So after all that protocol understanding and all that stuff, I figured out that you can actually also just copy all the pseudocode from Ghidra and then fix some of the type definitions in the pseudocode and comment out some calls to some external functions, and then you can actually just make it compile and then do it with AFL, and then seed it with 400 A's, and then, as you will see, it will give you a trigger for the crash in about 14 minutes, and with this, you can actually just start operating on the raw packet instead. As long as you don't change the length, but only change the actual payload, then you're past the protocol understanding yourself and can just work within the packet that this one has generated for you. So less thinking and more making the computer do the work for you. Big fan of that as well. So looking at it and how to exploit this memory corruption, it's pretty easy to trigger it. You just need to redirect to the shellcode, right? So very IoT-like. It's a bit like taking a time machine back to before exploitation mitigations was a thing. Back when I started hacking computers and everything was easy and fun. The heap addresses are not randomized or anything. Very sad. There's one call to malloc in the entire binary, and you cannot spray or place any data there. You cannot influence what it copies. So as a surprise, the device actually has address space layout randomization enabled, which means it reorders some things in memory. Something I cannot stress enough that you should always check is that even though it says that ASLR is enabled, you didn't build the kernel, so you don't know if it actually is enabled or if somebody has weakened it when they built the kernel in some weird way, because that is something that you will encounter as well, that even though it says it's enabled, maybe it's not. So as an experiment, I also wanted to see if I could find the ideal landing address that maybe pops up more often or after every device reboot or something, right? So I did some statistical analysis on the stack addresses, and my first run, I get a 1 in 1,000 chance of success, which is better than completely random, not very good, but then I run a bigger sample set, and you can actually see that this number coincides with the actual space of this the randomization space, because it's only these, the one that are listed as red here is the only things that are going to be randomized, right? So it is random, and you cannot magically guess it. You would need to find some other bug where you could leak some memory, but I wasn't in the mood for that exactly. So it's only the stack layout that's randomized, which means that you can do these return to libc style attacks where, because the base address of the binary itself isn't randomized, you can actually just land in one static location in the binary and then make it do something which is beneficial to you, right? So in this case, looking at somewhere good to land, because I've renamed things, everything is very readable, and there's something which will some functionality which is post-authentication in the service, because it also has some authentication module. But so I cannot just interface with the protocol and say, call this function where you start the telnet daemon, because then I would need to pass the authentication check, which I cannot. But doing memory corruption, I can actually redirect the execution flow to the place in the binary where it launches the telnet daemon and then access it that way, right? But it's a small binary, and there are no good pointers and so on and so on. Anyway, the best way, in my opinion, is to see if you can find some functionality that you can land in, and then that way you have taken care of ASLR, because the base binary is not randomized with that setting. So, I thought I had my shell, but I did not, because as luck would have it, the function calling spawning telnet is actually mapped at the one address range in memory that I don't want it to be at, because the function is at 001-3A58, and 3A means colon, and the scanf pattern is actually looking for the colon in the input. So if I supply that as part of the return address, it's going to get swallowed by the thing and not pop my shell. So that was pretty bad. But since it's actually an ARM processor, and looking at some more documents and whatnot, you can actually pop, on ARM, you can pop multiple registers in one instruction. So the pop instruction is actually an alias for load multiple and then some base register and then a register set. What that means is that I can land, I have a one shot of redirecting the execution flow to somewhere useful, right, where it does something I want with some constraints. But I can land at one address where it will do pop, where it reads a bunch of data from the stack and reads into actually the program counter register. And then I found out that the first 20 bytes of the packet that I have cleverly labeled auth data in the previous stuff is not subject to the scanf constraints, because it's not part of that part of the code flow, right? So I can land at this particular address and have it redirect execution to the beginning of the data that I sent, and then from there jump to the location where I actually want to land. And success, the telnet daemon is spawned, the service crashes, but it restarts on its own. So, you're not supposed to telnet to these devices, right? At least there are some ways to do it, but anyway, the telnet service isn't running, which means that changing the admin password in the UI will not change the root password. It is 123456. You cannot change it from a regular user context. You have to hack the device to be able to change the root password. And then you land in a restricted vendor shell called UVSH, which is probably Unit View Shell. And of course, the first thing you type in those is help, and then you look at the commands, and you can see that there's an echo command, and you can do command injection in it. So very classic. And then you can add a real root user that called toot in this case, that has a password of 123456, but which spawns a real shell, so that when next time you telnet to it and supply toot as the user, you get a real shell instead of this gimped vendor shell, right? So in the latest firmware, that one is fixed. The root password is still 123456, but they fixed this one. But the echo command is a monstrosity of the real echo command. So it actually, if you do echo-e, it's going to evaluate your characters and expand them. So you can actually still redirect output for some reason, and only in /tmp, but as luck would have it, there's actually production code in the temp folder. So you can override a script called killwatchdog, and then from the gimped vendor shell, you can try to do a system update of the firmware using TFTP, which will fail, but then it's going to spawn a reboot shell script, which will spawn the killwatchdog, which doesn't reboot the device anymore because I destroyed it. And then you have a real shell instead, and the watchdog is killed, and now it's no longer a camera, it's just a computer under your control. So, looking at how many shells you could pop with this, download all the firmwares, do some monstrosity like this, where you just unzip everything, pinwalk everything, grep for the byte patterns, and then you can make a list of vulnerable camera models and software releases, right? And then when you look at these, there's a few offsets for the desired offsets, or for the desired landing address, but try a few times because the daemon auto restarts, so it doesn't really matter. So I did an internet survey because you can actually provoke the device to give you a response without exploiting anything. And then, well, we just did an internet survey of the entire internet to find out how many of these are on the internet. When you send packets to port 7788, UDP packets on the internet, there's a lot of weird stuff out there because some computers just send you back the same response. Some send back, well, God knows what, right? But parsing the data we got back, you can see which ones are protocol compliant and give you the answer you expect. So we found 3,373 of these cameras on the actual internet, and you can't really do much with it without committing crimes, because what are you going to do? Log into them, exploit them? No. I think putting 3,000 of these very cheap cameras on the internet could mean that we have enough IPv4 addresses. At least if you can spare 3,000 of them for stuff like this, then I don't think we have a shortage just yet. They're placed very much where you would expect. Let's hope that they're not in government buildings in America, because going back to one of the original slides, it's actually not NDAA compliant because the chip is made, the high silicon chip is made from some Hikvision subsidiary or something, which means that it's banned in the government in America. If you look at who put these up internally, a lot of people have put them up, like ports and casinos and God knows what else. So I hope that these guys didn't put them on the actual internet. But of course, the vendor would like to tell you how great it is, so they show all the success stories. That's quite common as well when you audit products like this, that you can find who has deployed them just by looking at the vendor side. Another interesting conundrum, Uniview works as a white label camera reseller as well. So if you have a Panasonic Advidia camera, it's not a Panasonic camera, it's a Uniview camera with a Panasonic sticker on it, because Panasonic didn't want to go through all the hassle of writing camera software themselves, apparently, at least for this range. So it's clearly not just Uniview cameras that are vulnerable, it's also all these guys. So different logos and contents. If you want to see if somebody hacked your camera, well, very, very complicated, because you cannot see if the system is doing good or doing bad, and you have no runtime forensics capabilities. You have a not so good web UI, but that one doesn't show if there are hackers loose in it. You are logged out from the raw device access, so you actually need to hack it to see if you've been hacked. So that's a common, in my opinion, problem with IoT devices, that you have no idea what's going on inside. It's just a thing with a network plug. Things I skipped on purpose, anything that requires user interaction or man-in-the-middle capabilities, it doesn't interest me as much, because I prefer to be able to hack the thing on my own time and not wait for somebody to push some button, right? And I also didn't look at the peer-to-peer communication, because the cameras can actually communicate with each other if you have multiple, and then they can do some hocus pocus. It's normally quite a good place to look for bugs, because that's also very vendor-specific and not just some common component that they lifted from the internet. So I reported the maintain overflow to some third-party bug bounty platform, and I got $4,000, pretty good. I gave them to some cat charity, also pretty good, because I like cats. And I reported the rest of the issues I found straight to the vendor. They also have a bug bounty program, pretty good money, but 1 year of non-disclosure ties means that I wouldn't be standing here, for example, and I would have to keep it a secret or suffer a long list of consequences, which means that I didn't get any money because I don't want to have to keep something secret for a year for a little bit of money, right? It's, of course, totally up to you if you do something like this, what you want to do with it. But for me, it's definitely not worth not being able to discuss what I do for fun for some money, right? So, in conclusion, it's quite some work to be able to look inside the device, but it's also a necessity, and I think hopefully it's something that will get better with time, that you actually are able to look inside the devices without hacking them first. You should buy the devices. They're not. I think this particular camera, I paid 200 euro, but I talked to a guy who's actually a reseller of them, and he says he pays maybe 50, so they're not super expensive. If you're going to buy some camera stuff, I would actually still advocate that you buy something like this UniView stuff instead of Hikvision or Dahua, where the firmware is encrypted, and inside that encrypted firmware, there's another encrypted blob, and just encryption, encryption, encryption. And they will tell you that it's to protect their intellectual property, but I don't buy that anymore because there is no intellectual property involved in making an IP camera. It's a camera and a web interface, right? So the attack surface is not so easy unless you have a device. It's not so easy to map. I like the custom protocols. It's much more fun than web applications or the common components. And one last takeaway, I think that the OSS components you know and love, such as net SNMP, they can have been tampered with, right? In this case, it's leaking the password. That's not a default setting. Trust, but verify. And that was it.